horizons.
Thank you. Can you hear me? Okay. So thank you very much for the introduction. And I see that the gender is changed now, which is, no, but you see in the picture it is. So it's a nice touch. And okay. So I'm very happy to come here again for the second time. Last year, I actually learned a few things, so I'm hoping to learn a few things this year as well. And I think that the title of my talk and the subject of my talk is very relevant to this type of workshop. So I can start, right? It's okay? So maybe turn the lights here, turn off the lights a little bit. Just one row. Okay. No, too much. Yes, they will sleep. Okay. So yes. So the idea that I want to present is that the black hole, well, first of all, I don't like black hole singularities. You will see soon Wheeler, John Wheeler talking about that. And the idea is that in order to solve black hole singularities, we need to modify the state over horizon scales. And what I would like to do is convince you that this idea has some merit. And in addition,
also from people online. Are you invited?
This we had. No. This is. I think it's okay. Yes, he's. Yes. We checked it an hour ago. No, an hour and a half ago. Okay, so and then the point is that if this is true, if you need to change the geometry, the physics on horizon scale, this has specific universal observable consequences. Okay, so I'm not sure that I will get to this, but let's try.
For me, very hard to think of parts of the world that are taking part, acting, go to a place where they can't be seen or show anymore. The physical world is one, would be my way to put it. For me, very hard to think of parts of the world that are taking part, acting, go to a place where they can't be seen or show anymore.
So what John Wheeler was saying is that he doesn't like the idea that you get some matter in a smooth some smooth state, and it evolves into something that disappeared from our world. And this is very much in line with the ideas that I want to describe. If you think about it a little bit, it doesn't make sense. The idea that something just disappeared, the equations stop, and we don't know what happens. And the question that I will try to answer is suggest some ideas about what is the fate of this matter that collapsed. And when I say interior quantum structure of a black hole, I mean the state, the quantum state, the state of the matter that collapsed. I don't mean the geometry that we're used to call black holes. Okay, and it's roughly the region near the horizon. And if you want a visual aspect of what this is a would-be picture of a black hole, and this what's in there is what I call the black hole or the state of the interior. Okay, now typically people generally expect that quantum mechanics operates when curvatures are very large. So what this means is that the expectation, or popular expectation, is that it only becomes relevant near the singularity of the black hole. And because the curvature on horizon scales is very small, then the idea is that quantum mechanics is not relevant on these scales. And what I would like to convince you is that this is not the case, that we should think about modification on horizon scales if we want to resolve singularities. By the way, if you want to ask questions, there's no room for questions now, but later on, you're welcome to ask questions during the talk. And just as an advertisement, this is a visual clue of what can be learned if, or what can be observed if what I'm saying is correct. This is from a paper that should appear with Shania Vitan, who's here. Okay, I hope to get to it. And I guess I should thank Enrico Barose and Vitor for explaining to me what lab number is, because until a few years ago, I didn't know what it was. Okay, so let me explain now why we need the horizon scale modification to the geometry of the state. And the idea in this case is that the black hole is really a bound state of highly excited long strings. So, you can call it a neutral fastball or a string star. And in this case, the idea is that if you excite strings, if you heat them up, they become long, and they have lots of entropy. They're unique in the sense that their entropy is proportional to the length, and their energy is proportional to the length if they are free. And if they're interacting, so if they're free, their size is a random walk scaling square root of the length. And if they are interacting, they become more compact. And in this case, the idea is that this is actually what a black hole is. And what's interesting about this state of strings is that its equation of state is P equals rho in any dimension. So this is actually a very strange equation of state.
But they should decay. These strings should decay.
Yes, they will decay, and they decay by emitting small loops. But since this is not the main subject of my talk, I'm happy to discuss that. We actually evaluated this. I have a slide on it. They decay by emitting small loops at the rate of the Hawking radiation. This is just an introduction because this is not the main subject of the talk, but I'm happy to discuss that as we go along. So, and then the idea is that because the strings have so much entropy, the only way that they can become smaller is by cutting themselves. And if they cut themselves, their entropy becomes exponentially smaller. So the entropy, having maximal entropy, means that it cannot collapse. So the collapse is prevented by maximal entropy. Now, if I use the entropy bound, the first person who actually I know had this idea that entropy bounds or entropy can prevent singularities was Jacob Bekenstein in this paper from 1989. It's a wonderful paper in the cosmological setup. And we basically imitate that in the case of the black hole using a bound, an entropy bound that Gabriele Veneziano, who was, I think, the first director of the first scientific director of the GGI or some, right? And the idea is that each sphere has maximal entropy with the mass of a black hole of this size. And this is what prevents this state from collapsing. And it has to be on horizon scale. So from the center to the horizon, everything. And from this type of relationship, we can use standard thermodynamic relation to see that if the entropy bound is saturated, the equation of state is indeed P equals rho. And this forces the entropy, the energy density and the radial pressure to behave like 1/r squared. And you see that in this case, the mass actually fits the Schwarzschild relation. So each sphere behaves as if it has a horizon, gravity is strongly coupled, and you cannot describe it using classical geometry. And this is summarized in a series of papers, starting from our paper in 2016. And it's called the collapsed polymer model. And we've checked as far as we could that this object behaves like a black hole. But it's hard to do calculations in this type of setup. It's now we have advanced a little bit, so it could be, but so I'm trying to, in this case, present a geometric alternative, which I come to. But the idea is, now I can summarize the idea that what prevents a singularity. You see, if you think about matter collapsing, it's getting, first it's a white dwarf. So there's quantum pressure from the Fermi separation of electrons. Then it becomes, then gravity becomes stronger, and you have quantum pressure from the Fermi pressure of neutrons. And the idea is that there is a universal quantum pressure that can resist gravity for each value of the mass, and it's induced by quantum pressure of strings. Okay, so this is the idea, that there is a universal quantum pressure that prevents gravity from actually continuing the collapse once it reaches the horizon scale. And now to actually work with this type of idea, let me introduce the geometric analog of this maximal entropy, which is replacing maximal entropy with maximal negative pressure. So now, so I'm not suggesting that what's inside the black hole you will see is a fluid with these properties. It's just a way of mimicking what I described before, that each sphere is a horizon. And in this case, the singularity or the collapse is prevented by maximal mechanical pressure rather than entropy. And my claim is, as I will show you, is that if I take energy density, remember, the energy density was 1/r² LP squared in the previous example with the maximal entropy. So I keep that and I put maximal radial pressure. The epsilon here comes to regularize the geometry. It's something that we realized recently. And the transverse pressure is 0. And so it's a highly anisotropic fluid. And in this case, the scale of the object is slightly above the Schwarzschild radius, and you can create it at for any mass. So and this is actually also a requirement that many models that suggest alternative to black holes, they introduce a scale, and so they can get a star of this size only at one scale. But this you can get at any scale. And my claim is that this object looks from the outside, it looks exactly like a black hole. You cannot tell the difference unless you probe it some more. And you can see in this case that this type of equation of states evades a version of the singularity theorem that was established by Buchdahl, which is actually, if you don't know this paper, it's a wonderful paper. It's really a wonderful paper. It's the precursor of the singularity theorems, and it's much more physical. Yes. So it's actually, it depends on which observer sees it. From the inside, it's non-relativistic. It's you'll see. This I can compute, and in this case, what happens. So what the Buchdahl bound is saying that if you have a fluid sphere under certain condition, if it's bigger, if larger, if size is larger by a finite amount than the Schwarzschild radius, it's no longer stable, and you see the instability by having infinite pressure in the center. And he doesn't state it explicitly, but one of the conditions is having positive pressure. And it turns out that you need maximal negative pressure to avoid it, and you need it on horizon scale. So if you let the pressure be less than maximal over a finite range that is not perturbatively small, the Buchdahl theorem holds. So this is, again, it fits with the idea that you have to, in order to avoid the singularity, you have to change the geometry over the horizon scales. Okay, and this actually, there is something that I think is very nice to do. I hope I will get to it at the end, is to explain how this fits with the standard singularity theorems. So how having maximal negative pressure and horizon scale can avoid the standard Hawking-Penrose singularity theorems.
Just to
Yes.
bounce on assuming Las Vegas.
Yes, so I'm actually, that's why I said that it would be, to do something beyond that, we have to go to the formalism of the singularity theorems, but I think it can be done. It's actually a very interesting project to do, yes.
I wonder what happens, how this model can be fit in a dynamical situation with a gravitational collapse.
So that's another thing that is very interesting. And in fact, I think the fastball people, string people, maybe Massimo can help that. And since you asked, let me answer. But so the idea is, I think, first expressed by Samir Matur. So the idea is that matter collapses, and it needs to transition to this state when the shell or the matter reaches its horizon scale. Otherwise, causality tells you that you cannot get to this state. So when it reaches, and the idea is that when it reaches the horizon scale, a huge phase space opens up, the transition amplitude from the shell to each of the microstates of this stuff is e to the minus s, but the phase space is e to the s, and so the transition amplitude becomes 1. Now we are now finishing a paper showing that if you use a Euclidean version of what I showed you, you can do a Gibbons-Hawking calculation and show something similar to that. But it would be extremely interesting to take a string and see that the transition amplitude is no smaller than e to the minus s in this case. And I think it's a calculation that can be done, at least approximately.
Yes, one thing that I'm particularly concerned is what happens to the inner horizon, because you know that in a gravitational collapse, there is an inner horizon moving towards.
Yes, so the inner horizon is gone here because the geometry is regular. There's no, you will see. No. You will see.
Maybe.
Yes, you will see. Okay, so I just solved the Einstein equation with this condition of a radial p equals minus rho and p transverse equals 0. Very simple equations, spherically symmetric. We're now in the process of doing rotation. And in this case, these two functions are equal, and they can be expressed in terms of essentially the mass function, how much mass there is within a certain radius, okay? The standard Einstein equation, and the frozen star model, which we call the frozen star for a nostalgic reasons, because black holes were called frozen star before they were called black holes, and in this case, it's actually frozen. It's the most rigid object that you can imagine. The fluctuation is ultra stable. I will show it. And so, in this case, what I call the frozen star model is the choice f equals f tilde equals epsilon. If you're familiar with gravastars, then this choice is some other function of the radius, and the causal structure of this object is depicted here, where this is the would-be horizon, and as epsilon goes to 0, this horizon gets pushed to these two null lines. Okay, so this is a summary of what we learned so far. Each sphere is almost a horizon, right? Gravity is weakly coupled in this case. And we have a regular classical geometry, which we can now start to see what it means. So in fact, this is what it means. So if you think about what you need to get this type of geometry, if you have rigid strings with constant tension, this is what you get. And it's interesting that the tension is 8 pi g, which is smaller than Planckian tension. This is just a fact. And this picture is actually very instructive. It's a very good way of thinking about it. And you can immediately see that these strings are essentially completely rigid, so they cannot fluctuate. But we will see that. So the idea in this case is that this state of maximal entropy of highly excited strings is mimicked by a state of rigid strings, spherically symmetric rigid strings. Now, because let me show you. You see, energy density goes like 1/r², and it's finite at the Schwarzschild radius, okay? So what this means is that if I want to connect this object smoothly to the Schwarzschild geometry, I have to go from a positive energy density and negative pressure to 0 energy density and 0 pressure. Okay, and in the interior, there's in the center, there's a mild divergence because rho goes like 1/r², so the mass goes like r. So in the center, there's very little mass, but still we would like to have a geometry that is completely regular. And we were able to do that by just, again, we insist on solutions of the Einstein equation, no corrections, no. And we just modify the function, this radial and time function, such that it connects smoothly. There we introduce, well, this is a highly out of scale, a small layer connecting the interior to the Schwarzschild exterior. And this is how it looks like. The F starts from essentially, the F is the TT or 1/GRR. It starts at roughly 0, and goes linear near the horizon in the outside. Their density goes smoothly from some finite value to 0, and the radial pressure goes smoothly from some negative value. The only thing that happens there is that the transverse pressure becomes very large, and it becomes very large because of the conservation equation. It actually took us quite some time to figure out what the transverse pressure is, because we never talk about it in hydrodynamics. It's an interesting concept. Yeah, I don't have time to explain, but and you see, this is what happens in any, if you try to put any non-vanishing energy density, and it needs to go to 0, the Einstein equation forces you to have a transverse pressure, large transverse pressure. And this is the reason, by the way, in Gravastar, you know that you have to have negative energy. That's because the symmetry that they use is different, and that forces a shell of negative energy. Here is just positive transverse pressure. Okay, similarly in the center, we can go through a smoothing procedure. So here the function is slightly more complicated, but still a solution of the Einstein equations that smoothes out the geometry completely. And what happens there, again, the pressure, the transverse pressure is the one that is responding to this type of smoothing, but the null energy condition is still satisfied. So now, what I would like to show you is what happened. Mateo Monaco. Okay. So what I would like to show you is that this object is actually black. And because it's so simple, the geometry is so simple, I can just do textbook analysis of trajectories. This is the gravitational potential for null trajectories and for time-like trajectories. And the point is that the proper time for crossing this object is diameter over velocity, so essentially r over the velocity. But from an outside observer point of view, it's like this time is increased by 1/epsilon, because the redshift is very large everywhere. And so basically what happens is that an object falls in and it never comes out. If this epsilon is string, L string divided by RS or some other small quantity, this time is actually larger than the lifetime of the universe. So it's related to your question. So basically if matter falls in after this was already present, it just sticks to the edge because it takes so long to fall.
Why? Why isn't it all the website? No.
Yeah, no. It is log of epsilon, but it's a different epsilon. Yes. Yes.
So it takes a long time.
No, it takes a long time to cross.
So isn't that in some kind of probe approximation, like a geodesic approximation?
Yes.
So when you back react it, it'll take a finite period of time
Yeah.
and be absorbed into the structure. Look,
It's next. It's for that I need to do perturbation theory, which I'm doing next. Yes. Yes, but you see this thing, where is it? It's almost a horizon because this epsilon is very small, right? So a horizon in this case is just an apparent horizon. So when I take epsilon to 0, this is like a horizon. So I keep epsilon finite, but it's extremely small. So for practical purposes, this is a horizon. But no.
Because it's okay, I see.
Okay, well, they missed the question. What can we do?
Can I ask one more question? I thought there was a bound if I have collapsing matter where the smallest stable radius for my object is 9.8 GM.
Were you here at the beginning of the talk?
Yeah, maybe I missed it though.
Okay, so let me show you just the Buchtal bound. We evade it. This is the first thing that we check.
Okay.
And the reason is that we use negative pressure. So one of the implicit conditions in the Buchtal, and this was actually understood by Mazur and Motola. I had a big discussion with them.
Just wait the microphone, otherwise.
Yes, but the key element, that's why the Gravastar sort of solves it. We already said it. Causality prevents him from asking it again. So the key is negative pressure. And furthermore, I keep answering your question. You need it to be on horizon scale. If you let, for example, a shell, let's say half the horizon size be in maximal negative pressure and the rest normal pressure, the Buchtal bound holds. You can only let go, as I did, over a small shell, either at the outside or the inside. This we discuss at length in the papers. And I can explain to you some more. Yes?
Why don't you do that? You repeat the question.
Yes, I will repeat. It's for those of us who used to be at Erich's school, this reminds me of Zikiki saying, speak to the microphone.
Yeah. Probably
So just ask and I will repeat it.
Its connection to be so small. I mean, it can't be 1/10 or 100.
It's coming. So in principle, it can be.
Repeat the question.
The question was, why do I insist on epsilon being small? And the reason is the reason is that I would like it to be similar to a black hole. That's it. But yes, but okay. This was not a question, it was a statement, so I don't need to repeat. Okay, so
Actually, I don't want to refrain the enthusiasm, but the point is that you have say something like 11 minutes. So actually, don't forget that there is also discussion time.
yeah, but it's better to have this question.
For you,
and,
it's okay. Just
yeah.
okay.
So to summarize this, what I presented is an object that obeys the Einstein equation, is completely regular, has arbitrary compactness, epsilon can be whatever, obeys the null energy condition. As far as I know, it has no pathologies. It's ultra stable, which will come next. And as far as I know, it's the first example of such object. You can say something if you want. Okay, so now I'm coming to perturbations. Probably I will not be able to do that. Just let me know 5 minutes before, then I will go to the observable consequences very quickly. Yeah, yes, thank you. Yes, so now I would like to do perturbation analysis of this object. And because it's extremely anisotropic, it's not a standard perturbation expansion. The people who actually did that, it took us several months to verify that their calculation is correct. Were Doneva and Yazadaev in 2012. And so you start with a spherical symmetric background. You allow arbitrary perturbations, which are split into two directions, the direction of the velocity and the direction of the vector perpendicular to the direction, and this can also fluctuate. So they're not fixed. And we have this type of background. The generic perturbation equations, the generic perturbations are expressed in terms of the Lagrangian displacement vectors. And they have this form. And the special nature of the frozen star is expressed here. Delta rho plus delta p has to be 0, rho plus p has to be 0. And we use this notation to conform with this paper. And you see V and W are the angular expansions of the displacement vectors. Then we project the perturbation of the conservation equation on the two directions, and we get two equations. These are the same, essentially the same equations as Doneva and Yazadaev, and we have to apply the specific nature of the frozen star. And you see I crossed here from the equation all the terms that vanish. They're almost all of them. This term vanishes, for example, because P goes like 1/r squared. Then we need some kind of an equation of state, or something that will tell us what delta Q is. We don't have an equation of state here because Q is 0, and we have a different way of doing that. And when we do that, we see that the QDP is 0, and so delta Q is 0. And you see in this case that all the quantities vanish. So linearly, this object is ultra stable. It's completely rigid, exactly like a black hole. It cannot be perturbed. And then the idea is, because of what I described previously, is that if we include quantum mechanical effects, we would get in the string case modes with frequency that are suppressed. Nick, this answers your question. They're suppressed by G string square, which is a small number, but not extremely small number with respect to the standard relativistic waves. This is I claim that this is a universal phenomenon. And we can see that in the frozen star case, we need to deform the equation of state away from rho plus p equals 0 by something that mimics GS square. And when we do that, after we will go through some algebra, we find that the frequencies that we do have internal modes with frequencies that go like gamma square. You remember gamma was the deformation, the analog of the G string square, the deformation of the rho plus p away from -1. And you see that in this case, we get a spectrum of non-relativistic frequencies. And I claim that this is a universal result. And because I'm nearing the end, let me go to a short discussion of what it means for lab numbers. So you see in this case, if you have a spectrum of internal excitation, this means that when during inspiral, you can have energy transfer from the orbit to the internal structure. And this effect is enhanced in resonance. This is the paper that we are finishing with Shani. And the reason that you can get a resonance is, you see, you need the orbit frequency to match the internal frequency. The only way that this can happen while the inspiral is still on is if the internal frequency is non-relativistic, because otherwise it's too close. And because we have an internal spectrum that is non-relativistic, you can have a resonance during the inspiral. And what this means is that the accuracy that we can detect lab numbers is increased by 2.5 pn, right? From 5 to 2.5, because it affects, what happens is that this transfer of energy during the resonance affects the radius of the inspiral, and this affects the phase. So it's much better than tidal deformation effect that comes at 5 p.m. And the price that you have to pay for that is that you have to have a long inspiral, and that's why this is relevant for extreme mass ratio inspirals that Lisa can follow. And this is a figure explaining what are the values of the lab number. This is the quadrupolar electric lab numbers of the that can be detected, and you can see this is extremely small. With tidal deformation, you can hope to get to 0.1 maybe, but here you can get to values that are extremely small. Yes, so if I might, let me just say, so this is something that I think is interesting to do. And the key is to avoid the formation of a trap surface. And this is the idea that Matura had. Yes, so And this is also something that we do. And let me finish by showing my initial plan. And you see that we went through this subject. Thank you very much. Yes,
So
Vitor.
thank you so much, Ami, for.
I think it's not on.
Yeah.
Okay.
Try to tap on it. Yeah, it's okay.
Ah, okay,
Yeah, it's
good.
Slightly distracting. So I have a few questions.
Yes.
The first is the claim that the changes are on horizon scales. That is true, but it's a bit misleading because the changes in the external geometry are zero.
Yes.
You're still doing.
Yeah. I only mean in the interior. I was only speaking from the outside. It looks exactly like Kerr or Schwarzschild.
Yeah. Right. So my other question concerns stability.
Yes.
There's what I would say is strong evidence that any object whose surface lies within the light ring is going to be unstable, either non-linearly or maybe linearly if you start adding
So
rotation.
yes. So linearly, I think we close this. It's
Well, I don't think so because
Why?
you're freezing. You're totally freezing your object. I
No.
don't see an adiabatic index for your material.
What do you mean by in the?
I mean that it's very convenient that you're setting delta rho and delta b to 0.
No, but in this case, this is a result of a calculation. Yes, so, no, the perturbations are not spherically symmetric.
I don't understand how you define the anisotropy direction because.
Okay, so,
Away from spherical symmetry. how do you
yeah,
define it?
so. So this is not something that we did, this Doneva and Yazadev did. And the idea is, Yes, so you see these can fluctuate. Yes. No, the background, I take the background of spherical symmetry, but I have delta K is non-vanishing. Yes, but since you since you can fluctuate, also K can fluctuate. So what I do, it's true that I do the background, I keep spherical symmetric and with all the properties that I described, but the perturbation are, I think, completely general. We can discuss that.
Yeah. I think I agree with Enrico, actually. K is only well defined in spherical symmetry. So when you do fluctuations, I think you will have an underdetermined problem, but we can discuss that.
Yes, as far as I mean, we take into account delta K. So delta K itself, it's not seen, it's not us, it's done, but we can see that.
Question?
Yes. So
I have, well, actually I have.
yes.
So my last question is the love numbers. I didn't really understand what exactly is in resonance. The love number is defined as a static quantity. So zero frequency calculation.
Yes.
So what exactly are you resonating?
Yes, I went through this very quickly. Where is it? Okay. So let's see if I have. Okay, I don't have it here, but let me explain. So what happens is that the orbit is the orbit and the internal frequency match. So there is a resonant excitation of the internal structure. Now we can, and there is a phase shift because of that. And now we can relate this excitation of the internal energy to a static lab number property of the lab number, to the static lab number, which we did. This is you express it's a complicated process, but it's correct. You express the amount of excitation. You connect it to changes in the geometry, and then you can estimate it using the standard lab relations. So this is two papers that we wrote with Yotam Scherf. I think it can also be done in standard effective field theory diagrams, but we didn't do it like that. So you have a diagram essentially connecting the external lines to some internal excitation, and then you can connect the amount of energy that is that the internal structure is excited to the lab number. Yes, so this I know how to do. I can explain to you. And sorry, but I didn't have time to do that. Yes.
So there is a question over there.
Yeah, so I mean, clearly there's some parallels with the ideas, at least behind fuzzballs, et cetera. Right?
Absolutely.
And so so let me also ask you the same
Yes.
kind of question or problem that often is posed to fuzzballs. So you start with a very generic, let's say, top-down approach, right? And you have with your long string model. And then at some point you replace this or mimic this by your negative pressure. There was this nice picture of, the messy strings and then the radial strings.
Right, it is a nice picture.
Right. No, it's a very nice picture. And it also kind of maybe shows or maybe this is where the problem might be, is you're replacing something that is a typical state by something that is a very, very atypical state within this.
Yes.
Yes. So then my question is, the calculations that you then do with this very particular atypical state, how sure are you that these are representative for your actual underlying model?
Okay.
Right? Like if you say finite love numbers, et cetera, isn't this just an artifact of the atypicality?
Yes. So first of all, I think I agree with the spirit of your question. The point is that with this type of calculation, you can only learn a few things about what an external observer could observe. Okay. Now, with this, you cannot discuss any of the microset question. We can discuss, for example, this analog of the idea of Samir about the tunneling that we can do. Now, I think it might be possible to address some of these issues using an effective field theory of long strings, where you use as your variable the entropy density, which, if you remember, this is related to the winding mode condensate and so on. And we made some progress with that, but I think this is if you want to connect these two ideas, then the way to do it is write an effective field theory for the fuzzball or the long string in terms of the winding mode condensate. And then, as I always tell my students, the best way of solving a problem is knowing what the answer is. So, which is true. And so here I'm proposing an answer to these questions, and then it's much easier to go look for them in the more microscopic approach.
But because when you say, you expect large love numbers and also the internal modes to be subrelativistic, this is all based on the.
No, we found these we found in the string model.
I see. So this
using a free energy.
I see. So this is really based on the
theory, let's say. Okay, so
basically.
I can explain that. So largish love number is that if you have waves on the scale of the horizon, then you get love numbers of order 1. That is so this is the key to having that. So if the scale, in this case, you expect G string suppression, but it's still large. Okay, that's one. Now, non-relativistic waves, it's this is something that you can understand. It's because the redshift is large. So you have internal waves. They have wave number of order the size of the object. And now you ask what are the frequencies from an outside observer. They are non-relativistic. And this we actually, you can go through a general argument showing that. So I'm arguing that these two properties, the non-relativistic internal spectrum and a largish love number, are generic to any object of this type. So it would be, I think it would be very interesting to try and do it in the fastball context. And I think the calculations are not that hard.
So there is a question over there, and then
Yeah. Let's talk and.
Thank you.
So my.
loudly, please.
Yeah, I think so. Just in connection to that question, I think fastballs are related to extremal geometries, right? But in your case, you don't have any spin. So
Okay. So that's why I mentioned rotation. In fact, we're working on this now. We can't do extremal in this case. And in fact, the idea was to start with something that is as far from extremal as possible, because most of the objects that we have in nature are non-extremal. But I agree that it's very interesting to go to the extremal limit to connect with solutions that in the fastball context and also ADS-CFT and all of that. And it's actually, we started to look at that, and it's actually very interesting because of the high redshift, the actual rotation, any motion inside is suppressed. And so you get a very interesting object. And this is something that we are planning to do. I can explain more about what needs to be done in this case. But I agree that it's an interesting problem. You talk louder.
okay.
I will repeat
Closer,
the
yeah.
question.
Yeah, otherwise you repeat the question, please.
Yeah, I'm saying that said that love number goes to 2.5 PN, right? The love number you are
Yes.
measuring, it appears at 2.5 PN.
Yes,
But the tidal heating also appears at the same order.
5.
No, tidal heating.
Tidal
yeah.
heating, yes,
Yeah.
sorry.
So
Yes.
are you really measuring tidal love number or tidal heating? I mean,
No, in this case, it is a love number, and we actually in this calculation we claim that tidal heating is negligible in this context. But again, we can discuss that. So we checked that tidal heating is less important, but yes.
okay, thanks.
So if there are no further questions, I will run again. And